Hello and welcome to York Universe, the astronomy and astrophysics radio podcast, written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'll be one of your hosts this evening. I'm Dr. Elena Hyde, and I'm joined tonight by Maheen Hamani. We are broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. York Universe, I should say, broadcasts every Monday morning. It's late at night. Every Monday night at 9 p.m. local Toronto time, or Tuesday morning at 2 a.m. UT if that's more your speed. We are in conjunction with the online public viewing over on YouTube, and that's our York U Observatory YouTube account. So if you'd like to see any of the images associated with our wonderful telescope, you can always join us over there. And the links for that are, of course, on our main website, yorku.ca/science/observatory. You can navigate to our live show, find out more about the observatory, and of course, join the live chat over on YouTube. If you have any questions or comments about past shows, suggestions for future topics, or of course, anything else you'd like to mention to us, you can always contact us on observe@yorku.ca with our email. Now, we also have a social media account or two. We are on Instagram with York U Observatory, PixelFed over at the Fediverse at LNI Carswell Observatory, and Facebook at LNI Carswell Obs. You can join in and chat with us on all of these wonderful places. But if you are enjoying this program or any of our other work and would like to make a donation, that is up on our same website, yorku.ca/science/observatory. We will be monitoring the chat room for questions and, of course, always looking forward to peeking through the clouds whenever possible. Right now, the weather is, of course, the big problem in Toronto. It has been cloudy, windy, rainy, and snowy, and possibly hailing. How are you doing, Maheen? Is it doing all that the same things where you are?
I'm doing great except for the weather. It's been quite unpredictable, and so not only is observing difficult, going anywhere outside is in general very difficult, and you can't really see much in the sky either if it's so cloudy outside. So yeah, other than that, I'm excited for everything we're going to be talking about tonight, for which we don't need a lot of observing, at least currently.
That's true. We don't need to see much um, through the clouds. Although I will say for the observing fans in our audience, this week is a little bit of excitement because, of course, we do have the equinox coming up on March 20th. So if you're looking forward to the equinox or the equilux, which is just a little bit offset. That's equinox is March 20th, and on March 20th, as a fun conjunction and coincidence, we also have Jupiter and Venus very close together in the sky on that same March 20th evening. So just in case the weather somehow cooperates, it's definitely not doing it today. But on March 20th, you'll be looking for a super, super thin, just razor thin crescent moon, um, very low on the horizon next to a bright planet Venus. It should be absolutely spectacular in clear weather. There's also increased chance of aurora this general time of year. Um, due to the fun alignments that happen around the time of the equinox with the Earth's magnetic field and the Sun's magnetic field, and some other fun trivia. So, just in case the Sun cooperates and the weather's clear, there could potentially be some fun stuff to look for. In the meantime, I think we should probably console ourselves with something we can't see and therefore don't have to worry about the clouds for. Um, what do you think, Maheen?
I agree. I think going back into history, you don't really need to see anything.
That's true. Going back into history, we don't. And in particular, we're of course looking at lots of fun things involving dark matter this episode. And I think you have a great way to get us started in history. Do you want to go ahead and take us back in time?
Sure. Okay, so for our first item for this week in space/astronomy history, we have March 14th, 1879, which marks the birthday of Albert Einstein, an important figure in theoretical physics and someone you cannot finish school without hearing about. So he is relevant to astrophysics indirectly in many ways, but directly through his work on general relativity, which revolutionized modern cosmology. And more that I will be talking about as we go through this story. So in this section of the astronomy history, I will walk listeners through his very eventful life, and the discoveries he made in physics. Einstein was born in March 1879 in Germany. He had demonstrated a passion for science and music early in his life growing up, which led him to study physics and mathematics at the Swiss Federal Polytechnic School in Zurich in 1896. Despite being known as a genius today, he was unable to secure a research/slash teaching position after graduating. Instead, he started working at the Swiss Patent Office as a technical expert in 1901. In hindsight, this gave him extra time and opportunity to explore his ideas in physics on his own, which led to the year 1905, often known as his miracle year. So in 1905, he published four of his groundbreaking papers that have led to research that is fundamental to physics today. So his first paper was on the photoelectric effect, suggesting that light consists of discrete, localized energy packets called photons rather than just waves. This work helped found the quantum theory and became the basis of his Nobel Prize in Physics in 1921. His second paper was on Brownian motion, in which he analyzed the erratic movement of microscopic particles in a fluid, helping move the theory of atoms to a reality by allowing scientists to observe their behavior during experiments. The third paper introduced the theory of special relativity, proposing that the speed of light is a constant regardless of the motion of the light source or observer, while space and time are relative to the observer's motion. He also suggested that the laws of physics are invariant in all inertial or non-exhilarating frames of reference. His fourth and last paper of the miracle year gave us the famous equation of energy mass equivalence, E is equals to mc squared, suggesting that a body's mass represents its energy content. This sounds like the work of someone's entire lifetime, but he got all of this done in a year, so that's quite interesting and creates a lot of pressure. But moving on, by 1908, meaning just in 2 to 3 years, his groundbreaking research aided his transition back to academia. And despite his initial struggle to get an academic position, he later took positions in Bern, Zurich, and Prague, and he was later appointed the director of the Kaiser Wilhelm Physical Institute at the University of Berlin. Another groundbreaking work that came out of Einstein's life was his theory of general relativity, published in 1916, in which he defined gravity not as a force, but a curvature of space-time caused by mass and energy. A few years later, in 1921, he won the Nobel Prize. So it took quite a while for his work to be recognized in a way that it led to the Nobel Prize. For his services to theoretical physics and especially his discovery of the law of photoelectric effect. And in the early 1930s, he accepted a position at the Institute for Advanced Study in Princeton, New Jersey, formally retiring from that position in 1945, and still continued his work until he died 10 years later in 1955. So, a great time to celebrate his birthday, which was 2 days ago.
Wow, yeah, as you say, just a huge amount of really game-changing results for physics as we know it today. Um, and it's really interesting whenever we talk about kind of the history of physics, and Einstein rightly gets quite a lot of credit for those discoveries. But it is also worth noting that at that time in 1905 and before and after that, there was also a lot of uncredited work being done, and there's still debate today over whether or not his wife at the time had actually contributed on the papers because she
Mhm.
actually had an academic career um, when she had it disrupted, shall we say, by becoming pregnant, and a lot of her work overlapped with his in interesting ways. That's been sort of listed as it does seem like there is some evidence that she was involved in several of the papers. To what extent, we may never know. But it's a really interesting case of you don't always see everyone behind the scenes.
Hmm. Yeah, this actually reminds me of having read about her where I think she was a mathematician, so her math skills were stronger in a sense because she was Einstein's classmate at the time. And she had been involved in deriving the equations for general relativity or special relativity, either of those.
Well, there's a couple interesting ones, and it's so the one I'm thinking of is Maria and it could be no Mileva Maric. So she was married to him for I believe about 16 years or so, which went through that kind of most productive period. He did marry someone else after that, um, who was not an academic. But yes, she was a major academic force in her own right. Not so much published or getting any academic positions out of any of this, though.
Hmm. I guess it
But
has
yeah,
to do with the time and how uh, the academia wasn't as open for women at the time. So,
yeah, I think there's a quote from her somewhere that goes something like in one of the letters, it was something like, all those papers we worked on together have made my husband famous, or something like that.
mhm,
But yes, you know, it was quite a challenge to get your own name published. People were, lots of women were publishing under pseudonyms in other ways, but in this case, it's always interesting to note that especially at that time, there's a lot of people doing a lot of work behind the scenes that you don't always see.
it's also just very hard to prove this unless the person who has published the paper says themselves that they have taken help from these other people and give them their own, ownership on it. But Einstein's not here anymore, so unfortunately.
Yeah, and the history of physics is full of, as they say, hidden figures, which I believe was a movie at some point.
Mhm.
Um, and you know, but all these discoveries have made their way into science as we know it now, really affecting how we think about space and time and energy and matter, and that gets me to dark matter. Um, because of course we are somewhat dark matter themed here, and I want to take us back not so far in history. So I have a much more recent historical result. This is just from a few years ago. So March 21st, 2013. I was just, oh, it's just 2 or 3. That's okay. So it's more than 10 years ago. Sorry, I'm old. I might also be out of podcasting practice. Um, so March 2013, the on the 21st, which is a few days from now, a few years ago, the Planck team released its first all-sky map of the cosmic microwave background radiation. And the cosmic microwave background has been a interesting feature of cosmology. It is, part of this idea of a perfect universe discussed by Einstein and many other philosophers, actually. Philosophers, scientists, everyone's very interested in the beginning of the universe. And is there such a thing as perfection? Well, we get to be perfectly imperfect because the Planck measure of the universe produced this beautiful all sky map. And the 2013 data release was the first, not the only and not the latest, but the first all sky map of that cosmic microwave background radiation. And it really impressively confirmed the standard model of cosmology set up by the framework that Einstein put together, basically, with a bit of help from various people, credited and otherwise. Um, so we have this really interesting idea that the universe, everything we know in every direction that there is, used to all be much, much, much closer together. And as it was much, much, much closer together, it was very, very hot. Originally, some people thought that this must be some kind of uniform condition or that there would be some perfection that could be mathematically described. But there were little tiny anomalies and inhomogeneities. So this was really interesting. Do we or science, do astronomers understand the universe? And do we understand how it might have begun? So the Planck revelation of this almost perfect universe put all kinds of questions into physicists and astronomers' brains and many other people's as well. Everyone got very excited looking at the anomalies and inhomogeneities. That's a hard word to say. Um, Looking to see how our model of the universe might change and what kind of importance would things like dark matter and dark energy actually have in the universe. And when we say dark matter in this case, I'll just take it to mean things that are not matter like we know it. So normal matter, making up galaxies and stars and the Earth and, I don't know, root beer floats and hamburgers, whatever you want. All that stuff, normal matter, unless you're very unlucky. But no, it's all normal matter, things that we know of, called baryonic matter sometimes. But all that stuff in this original analysis seemed to be only about 4.9 to 5% of the total sort of budget for mass and energy in the universe. So originally, this would mean that 95% of the universe would be things that we didn't know. And that's really exciting. There have been all kinds of estimates that have happened since then. The one I have read most recently was that people saying about 27% of the universe may be dark matter. Um, the Planck mission really took everyone up, brought the universe into focus, I suppose, as it was not before, and so it gives us a lot of great things to debate about. The map, of course, measuring temperature variations, and this is a cool thing. So the Planck team, when they were looking at the entire sky, they looked every direction they could, and they tried to measure variations of temperature on a very, very, very accurate scale. And once they released this most accurate and detailed map that, from 2013, they've done better ones since then, but they were able to change some of the concepts of the time. So looking at things like the oldest light in the universe, um, this is, of course, giving us ideas about age, um, contents, origins of the universe. And Planck was, or is, was. I should check if it's still going. No, it's not. But Plunk is a European and consortium mission. So Plunk was and is running up in space. It officially ended in 2013. And I can't remember if they deorbited it or not, which seems like I'll leave that question to our viewer, our listeners. The deactivation happened in 2013. I don't remember if they deorbited it, but the data that they achieved showed that the universe was expanding more slowly than they originally thought. And the first age revision that they did in 2013 pushed the universe to an age of 13.8 billion years old, which was 100 million years older than previous estimates, which is just ridiculously old. So they keep making adjustments since then. But in 2013, what they saw was less dark energy, more matter, both normal and dark matter, than had previously been known or thought in the models. And, this dark matter in the universe, we still don't really know what it is. We know what it isn't. It isn't matter like we know it, but it's some kind of invisible substance that can only be seen through the effects of its gravity. And while coupling or relationship with dark energy is under debate, I think we might talk a little bit about that later. Um, there's all kinds of really strange things that start happening when you talk about objects in space that are made of things that you don't know what they are, but you know what they aren't. So the nature remains mysterious. And there's a great quote that actually happened in the 2013 release that I thought I would add in here. And this is a quote from Charles Lawrence, the US project scientist for Plunk at NASA's Jet Propulsion Laboratory in Pasadena, California. He says, as that ancient light travels to us, matter acts like an obstacle course, getting in its way and changing the patterns slightly. The Planck map reveals not only the very young universe, but also matter, including dark matter, everywhere in the universe. Ooh, so if you want to read more about Planck, the website is still active. The spacecraft is not. So just to make sure I get that correct. But it is, you can actually go and search the map online. It has a lot of wonderful science results that have come out. The last official data release was 2018, which I'm sure the keen eared among you will note that that is several years after the spacecraft got turned off because it does take some time to practice and process this data and make sure that all your results are precise. So you will find all of the most accurate last results in the 2018 final data release, not the 2013 one. And most of those measurements have error bars that are really, really quite small, which is very impressive. And they give things like values for the Hubble constant, the age of the universe, and it gives lower and upper limits, still around 13. So, if you say around 13 billion years, not too wrong. Anyways, dark matter, very fun.
This is so interesting. On the note of cosmic microwave background, it's always so fascinating to me that something like microwaves can give us so much information about the early universe and all of these constants. It blows my mind.
Yeah, it's really quite interesting how the science has come together on it. And of course, the Planck spacecraft was a quite a marvel actually when it came together. And its instruments had a low and high frequency bands. um, their their construction is very, very different from what you'll see in things like optical telescopes. They do really look very sci-fi. In particular, that one of the instruments actually has kind of like a little horn attached to it. Like if you imagine a trumpeter trumpeting, it kind of looks like that. Really great, really wonderful instruments, really cool science. And speaking of wonderful instruments and cool science, I think you have a pretty interesting instrument to talk about too.
I do. So, I found a very interesting astronomy history item, also from more recent history, inspired by Dr. Hyde. So this is from March 14th, 2023. And for this story, thanks to our OPV crew, you should be able to see the image of a star called the Wolf-Rayet 124, which I'll talk about in a bit. And for those listening to the podcast recording on Spotify or any other place where you get your podcasts, if you're interested in looking at this image, you can go to our recorded OPV stream from March 16th, and you should be able to see this image. So this is related to a rather recent space history story, which is, as I said, from March 14th, 2023, when the James Webb Space Telescope released an image of a rarely seen phase of a star's death, which comes just before it goes supernova. Um, Supernova, just as a reminder, is a luminous explosion that occurs in massive stars when they die. And when it comes to the Wolf-Rayet phase, it is the time of the evolutionary cycle of a star that the JWST was able to capture. And this is known as the Wolf-Rayet phase, um, which gives it the name of the Wolf-Rayet stars. However, this is something that is observed only in some massive stars. So it is not a very widely seen phenomenon. It's more of something that is seen only in a few select massive star, or at least has been seen so far. And essentially, this is a brief stage where massive stars cast off their outer layers before exploding, resulting in their characteristic halos of gas and dust to frame around them, as you are able to see in the image. And the rarity of this event makes its detailed observation by JWST especially valuable to astronomers. So the stars that they captured an image of is 15,000 light years away in the constellation of Sagitta. I hope I'm pronouncing them correctly. Their powerful infrared instruments help reveal exemplary detail of the distinctive halo of gas and dust that frames the star, showing its history of episodic ejections throughout this phase. And it had shed 10 suns worth of material so far. So I believe it weighs about 30 times of the mass of the sun, and so it has shed about 10 suns worth. So this phase is still going on. And the gas ejected moves away from the star and it cools, leading to the formation of cosmic dust. So, such dust is obviously of special interest to astronomers because if it survives the supernova blast, it could contribute to the universe's overall dust composition. And this is because, according to our current estimates, there's more dust in the universe that then can be explained by current dust formation theories. And so one can say that maybe Wolf-Rayet stars are what play this role in identifying the origin of where this surplus dust is coming from. Maybe it's coming from Wolf-Rayet stars. And so this also makes the benefit of James Webb prevalent to us when it comes to astronomical observation, because before Webb, there was not enough detailed information for the exploration of dust production in environments such as this specific star. And with Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, a balance in the brightness of the star and the naughty regions in the fainter surrounding gas is achieved, and the clumpy structure of the gas and dust nebula is revealed, which is very useful when it comes to astronomers trying to study the dust composition and what these halos of gas and dust around the star look like and what would we expect once the star goes supernova. So I thought that this was quite interesting.
Oh yeah, absolutely. And these hugely unstable stars, and could create quite a lot of mess. And they're also listed as, extremely rare just because they're so unstable they can't survive
Hmm.
long in that state. But yes, very, very interesting, very, very interesting beasts. And the fact that it was observed by JWST, of course, means that there is a fabulous picture to go with it. So I'll make sure to put that as the descriptor image for this podcast. All right. So JWST has really outdone itself in so many ways. This is probably just one of them. But I will just go ahead and give a little extra shout out because, of course, JWST has also recently been looking at making, helping to make higher resolution maps of dark matter in the universe. I think it's well over 800,000 galaxies in their map now. I'm not sure the final count, but it is interesting that in a lot of cases that we're talking about dark matter, we're now talking about things, regions of space that have a defined extent. So there's a volume, there's a mass, and we still don't know what it is. One thing that might help is a partner to JWST that's coming online soon, we hope. It is the Vera Rubin Observatory. So I'll just give a little shout out to, and again, joining Maheen here in the recent past, we are living in history, folks. 2025, last year, March 12th, the Vera Rubin Observatory achieved a major milestone towards becoming fully operational. The Vera Rubin Observatory is, a really exciting new, not quite fully done telescope in Chile that's being built. It was formerly called the Large Synoptic Survey Telescope and was renamed to the Vera C. Rubin Observatory, also just called Rubin Observatory for short. It's atop a mountain in Chile, and it is nearly complete. They've been working on it for quite some time, but it's going to be using the largest camera ever built. I suppose this is a Guinness World Record or challenge somewhere. But it will repeatedly scan the sky for 10 years as in its mission, creating ultra-wide, high definition time lapses. And this is a large field of view, huge, massive project. It is going to create a very big data problem. But fortunately, we have processes, mostly thanks to radio astronomy, actually, for dealing with even petabytes of data at a time. And yeah, so this telescope has been really, really interesting for quite some time. It had its first light in June 2025. The history of March 12th is actually the installation of the LSST camera on the telescope. So this was its one of its biggest milestones. This is the final optical component that they needed for that telescope. And then it got to enter the last phase of testing um, before capturing, of course, its first look images. And then they're going to start the legacy survey of space and time, which is a cool name for a survey, the survey of space and time. So they've given it, there's caution to all acronym lovers. There are several LSST type of acronyms in here, so watch out. The camera that was installed in 2025 is the largest digital camera ever built, and they are claiming that. So if anyone knows of a digital camera larger, I suppose please put that in the comments and email me. Actually, I would love to know about that. This camera weighs over 3,000 kilograms. It is 3,200 megapixels, and it is at the center of the Vera Rubin Observatory optical system. So the optical system is a sort of what you think of as a regular optical telescope. It has a 8.4 meter mirror, and it looks a little bit like our 1 meter telescope on campus if you've ever been to see it. It has a primary mirror and a secondary mirror, but it has some real innovation to its design that makes it a cut above, not just the fact that it's 7.4 meters larger than our our mirror on at York. We have a 1 meter telescope. The design means that it can actually capture at the same time, simultaneously, faint objects and objects that change in position or brightness with anywhere within its field of view. So this camera, the goal is to repeatedly scan the southern night sky due to its location, and they're going to do it for 10 years, they hope. Fingers crossed, funding allowing. This will create an ultra-wide, ultra-high definition time-lapse record of the universe. And of course, if you're excited about that, they're expecting many, many, many discoveries of asteroids and comets and pulsing stars and supernova explosions, and of course, all kinds of discoveries around microlensing and potentially structure of dark matter, maybe. But I think the thing I'm most excited about will just depart from dark matter slightly and say that it's actually, this is the southern sky, so it will be pointed towards Proxima Centauri, which is the closest star to our sun. I've always been a little bit just fascinated by that. All right, so that's the that's the end of the history section.
This makes me think of NearCam on JWST. It's 40 megapixels, and the kind of images we're getting from it are mind-blowing. So I wonder if we put the camera as big as of the Vera Rubin Observatory or the telescope in space, like what would that give us?
Yeah, that would be very, very, very interesting because it does weigh over 3,000 kilograms.
Mm-hmm.
So um, launching over 3,000 kilograms would be a challenge, I think, to launch it without breaking it. But you know, if we did, maybe you could launch it in pieces and have someone build it in space. That would be pretty cool.
I thought about that, but JWST itself weighs 6,500 kilograms, so I guess like it would add up to even more, but if they can do this much, maybe they can figure that out too.
Yeah, well, if you wanted the whole Vera Rubin Observatory, you need the 3,000 kilogram camera and then the 8.5 mirror and the rest of the assembly.
That's true.
Because the camera would be awesome just by itself in space, but it wouldn't be quite as awesome if it didn't have a telescope behind it. That said,
Hmm.
I do think they're going to be doing some pretty fancy adaptive optics processing. I think I saw that somewhere. I haven't heard, um, but yes, they are doing some correction, but this large of a field of view. That's what I remember seeing. Because the field of view is so big, you can't use regular adaptive optics to correct for atmospheric seeing. So yeah, there's a great reason to launch it into space.
I'm just a little worried about ground-based observing in general because of a lot of satellite launches coming up, or possibly
Yes.
coming up. So yeah, I don't know about the future of the Rubin Observatory or astronomy ground-based. I hope that things don't go out of hand with these launches.
Yeah, well, I think, we've all been seeing more and more of the Starlinks come up, and of course, the Starlinks come down. We had one famously crash into Saskatchewan. They were finding debris all over. They're coming down at a rate of about 3 to 5 a day, I think I read.
Wow.
Um, but they're launching so many more. There's a real risk of creating a massive debris field around Earth, and I think that's something we've talked about before on the show, but Just in case anyone wants to look it up, there's a theory that a mathematical model that shows that once you get too many things in Earth orbit, the collisions between those things will create so much debris that it'll just be collisions all the way down. So one satellite crashes into another, the debris field crashes into 12 more, those debris fields crash into 1,000 more, and pretty soon you've just got a debris field surrounding Earth. So that's called the Kessler syndrome, and it's been modeled at least since the 70s, I think. Um, so we know that this is a bad idea.
Yeah.
Oh, I should do the reminder before we get too far. Um, Everyone, it's a little past halfway. This is the reminder that you are listening to York Universe, broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. If you're enjoying this podcast and would like to check out more of our awesome programming or come in person for tours every Wednesday, you can check out our website at yorku.ca/science/observatory. Tonight, you are listening to Maheen Himani and myself, Dr. Elena Hyde, and we're talking history and dark matter and recently a little bit of satellite collisions. Um, just as an extra reminder for this halfway sparkler, if you would like to check out any of the viewing, the online public viewing that runs concurrently with the live portion of the podcast, that is on our YouTube channel, which you can navigate by going to that same website and searching for OPV or clicking on any of our YouTube links, or just go to YouTube and type in YorkU Observatory. All right, so let's get to some news. We're a little bit past the halfway point. Oh, I do have to give an announcement as well. I forgot about the reminders. We have a little extra reminder to all of our astronomy fans. The Astronomer in Residence program is open once again. That's right, it's 2026 and we're doing it again. So this is the fifth year we've run an Astronomer in Residence program with the Allan Carswell Observatory and Killarney Provincial Park in Ontario, Canada. What is it? Well, we send astronomers out to the certified dark sky preserve of Killarney Provincial Park during the summer months because it is too cold in the winter in Ontario. And those astronomers run programming well at the park. There's a observatory on site, and we help run that observatory for the parks in the summer. You deliver tours, give talks, go on hikes if you like. And of course, if you are camping out in that general area of Sudbury slash Killarney and beyond, feel free to stop by and check out the telescopes and do some viewing with us. We have solar viewing and, of course, lots of wonderful evening programs. The blogs of all of our astronomers are on that same website, so I won't give it to you again, but it's under AIR for Astronomer in Residence. Lots of wonderful students and grad students and RASC Toronto members and other RASC members. Many astronomers have made their way out there too. And if you would like to join them, the applications are open until the end of April for the summer months. If you missed the 2026 season, you can always join as visitor or apply again in 2027. Limited spots, so very exciting. Fifth year running. Check it out. And of course, the Wednesday tour will be happening this week as well. Okay, so that's all the news that's fit to print. That's all the news from the observatory, I should say, that's fit to print. We have some other news that's a little more topical. Maheen, do you want to take us into the rest of our science news area?
Sure. So, diving right back into some dark matter related news, we're going to be talking a little bit about the mysterious gamma ray glow coming from the Milky Way's core, which is thought to potentially be dark matter. So, towards the end of last year, evidence was found to suggest that the mysterious glow observed at the center of Milky Way could be the evidence for dark matter. This diffuse glow observed is that of gamma rays and has confused researchers for decades. So this has been observed. We just don't know what it is. It has been a mystery for a while now. And we don't know what the causes of these intense, excessive emissions that we are seeing from Milky Way is. So it is believed to be caused either by the collisions of dark matter particles or potentially quickly spinning neutron stars, which are also known as pulsars. So if pulsars don't resolve this mystery, proof for the existence of dark matter may become plausible. So recent research supports this claim by using supercomputers to create maps of dark matter location in the Milky Way while taking into account the formation of the galaxy itself. So as some of you might know, when we're trying to study things that we can't necessarily resolve through observations, we use supercomputers to run our theoretical models, and get a better understanding of whatever we're observing within the observational side of astronomy theoretically. So this is something this research group did. And since they took into account the formation of the galaxy itself, it increases the accuracy and therefore is quite valuable as galaxy formation itself guides and influences how dark matter is distributed within the galaxy. So this work was a collaboration between researchers from Johns Hopkins University and the Lebanese Institute of Astrophysics Potsdam. These maps point to the fact that there are increased collisions at the center of Milky Way due to them being gravitated towards the center of galaxy and clustering. So during formation, due to intense gravity towards the center, the dark matter particles, as Dr. Hyde had mentioned previously, influenced by gravity, known only through gravity, are pulled towards the center of galaxy and they cluster. So this also suggests an increase in their collision at the galactic center because that's where they are the most intensely located. So, by factoring in realistic collisions within their simulations, they found that their maps matched the gamma ray maps taken by the Fermi Gamma Ray Space Telescope. And this finding supports that the dark matter collision theory is more plausible over the neutron star theory. And the reason that the neutron star theory is weak is that a great number of millisecond pulsars, or fast spinning neutron stars, um, then are actually seen would be required to make the calculations of gamma rays observed work. So the amount of or the intensity of gamma rays observed does not match how many pulsars we have observed so far. And so it doesn't add up based on our current observational data and evidence. And so, in order to further explore this mysterious glow at the center of Milky Way, researchers are waiting for the construction of a huge new gamma ray telescope called the Shrinkov Telescope Array. And due to its high resolution with the capacity to measure high energy signals, the breaking of this paradox between these two options causing the glow will become more likely. And this is because the energy of the gamma rays received will provide insight into its source of either high energy pulsars, because pulsars would produce more high energy gamma rays, whereas the dark matter collisions would produce more low energy gamma rays. And if we can figure out what the energy of the gamma rays received are, we could either narrow out that it's one or the other, or we might find out that it's neither, and we have a bigger problem to solve. But this is something to wait for until we get this telescope running.
Even so, I'm sure the theorists are going to go full speed ahead because this is so cool. The idea that we could have a alternate um, an alternate explanation for the center of our own galaxy. After all this time of studying the universe and starting to think like maybe we actually know what galaxies are doing. And then what if there are dark matter particles colliding in the center of the Milky Way's core? It's so cool. And I just give a little shout out to, because you mentioned, gamma rays, it's worth noting that these radiations are very, very different. So from what we experience here on Earth, they will not turn you into the Hulk, but they are tiny, tiny wavelengths. So when you talk about light as we know it, it's pretty small. Light that we can see is a couple hundred nanometers, 10 to the minus 9. But you get, of course, light wave at different sizes corresponding to different names. So if you make the waves very, very big, you get radio waves, which we listen to. So here's our radio podcast. If you make them very, very small, so much, much smaller than visible light, you get ultraviolet, and then you go even smaller, you get X-rays, and then even smaller, you get gamma rays, which are these super tiny wavelength, high, high, high energy objects. And this is what they're seeing coming out in unusual numbers. I'm so glad that you mentioned this article because it's really related to the one I wanted to talk about. Because there are other ideas that have come out recently that show that maybe we could think about the center of our Milky Way as a dark matter object. So this is from last month, February in 2026. For many, many years, decades, the motions of the stars near the center of the Milky Way galaxy have been followed. And it was very clear that all those stars were moving around something that was we couldn't see and that was fairly small and really dense. And so people said this is clear evidence for a supermassive black hole. But there's a new study out from Valentina Crespi and the Institute of Astrophysics La Plata that actually theorize that there could be a very different kind of compact object, basically a self-gravitating fermionic dark matter object could be compact enough to reproduce the same stellar motions that we've been seeing all this time. Um, and if that is a dark matter object, it would actually go some way to corresponding with the idea of dense dark matter particles. And there's all kinds of really interesting possible crossovers you get when you say, okay, well, um, how much, how many black holes could be dark matter? Could they all be dark matter? Is this a whole new thing? There's a lot of really, really interesting theories that have happened. We are still very, very much waiting for more observations, not just, of course, the new telescope that Maheen mentioned, but also, of course, this February 2026 paper does say that we really need to look at the modeling that's come out of the Event Horizon Telescope. And one of the things that has already come out is that dark matter cores, if it is a dark matter core, would cast a shadow-like feature similar to the one imaged by the Event Horizon Telescope, which is now the famous black hole shadow image. So really, really exciting times we live in here.
Yeah, I think what I love about these kinds of things is like the unknown nature makes scientists so creative and they come up with all these different kinds of dark matter that you can't even keep track of. because there's just so many, and how they're then related to the central black hole, or how the galaxies formed, or what the early universe looked like, and it's very fascinating.
Oh yes, there is no lack of things to study, folks. It's, if you ever think there's any possibility of astronomers getting bored, I can say it's absolutely zero because there's always something amazing happening. And right now, this is a whole new area that people are really having a lot of fun with. Now, speaking of having fun, I think you've got one more news item. Do you want to go ahead with your dark energy?
Sure. So, towards the end, we are leaving you with something completely different from dark matter. So, my next news item is about dark energy. And just to clarify, the only thing common about dark matter and dark energy is that they are both mysterious and hence the name dark, but they're not the same thing. So, don't confuse them as being the same thing. Um, so recent results from the dark energy spectroscopic instruments are giving astronomers new insights into the mysterious force, which, as I said, is known as dark energy. DESI is an international project designed to map the large-scale structure of the universe by measuring the positions and distances of millions of galaxies and quasars, creating one of the most detailed three-dimensional map of the cosmos ever built. By studying how galaxies are distributed across billions of years of cosmic history, scientists can track how quickly the universe has expanded over time. And early analyses of the DESI data suggest that dark energy may not be constant, as previously assumed in the standard cosmological model. So this has been more of a known kind of a fact that you would study in a standard cosmology class, that dark energy is a constant. However, these analyses from this model now are predicting that that might not be the case. And instead, the data hints that the strength of dark energy could have changed slightly over the history of the universe, possibly becoming weaker in more recent cosmic times. And if this result is confirmed with additional observations, it would be a major development in cosmology because current models generally treat dark energy as a constant property of space. And a changing dark energy could alter predictions about how cosmic expansion will behave in the distant future and may require us to revise parts of the current model that describes the evolution of the universe. So I guess it is important and is emphasized that these findings are still preliminary and that DESI will continue collecting data over the coming years to improve the precision of the measurements and determine whether the trend holds. But still very exciting and could uncover something completely new when we consider the expansion of the universe and dark energy.
Absolutely. And of course, there are still some people arguing for the coupling of dark energy and dark matter. I don't believe it, but but it is really, really interesting, and I'm so glad you mentioned the DESI data. There's a lot of really interesting things going on with the Dark Energy Spectroscopic Instrument, or DESI as it's known. And I'll just go ahead and end off with one final little fun thing to wrap back in dark energy and dark matter. If you want to see one of the coolest, newest, and this is really brand new, dark matter maps. There's a brand new one out right now from the Cosmos Web Survey. So it's a JWST plus Cosmos Web. And this is a combo map using Hubble Space Telescope data. And as part of this giant sort of survey, looking at weak lensing mass, gravitational fingerprints, filaments, clusters, voids, and looking at the hidden scaffolding that shapes the visible universe. So this map is out now, 2026, I had to look at this, 2026 March. So if you're very keen, you can go and look it up. Very fun stuff. Unfortunately, we are just out of time. So we'll have to leave you all hopefully wanting more. I know I am really excited to see what comes next. All right, everyone, you have been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Maheen Hemani and myself, Dr. Elena Hyde. You can always connect with us on social media. We're on Instagram, Facebook, and PixelFed. And of course, check out our website for show notes, content, YouTube programming, uh, podcast links, and of course, free tour tickets, yorku.ca/science/observatory. Thanks for tuning in to York Universe, everyone. Clear skies and have a good night.
Have a good night.